All right, welcome everyone. Thanks for tuning in. This is another exciting learning lab. I'm really excited about this one because we're going to be talking about a lot of cool things. We're going to be focused on hierarchical forecasting, which is a situation that I'll explain a lot more in detail as we go through the business problem this week. But basically what it is we've got a lot of different products and they kind of roll up into different groups, different departments, different stores, different states, and then the total aggregation. And we want to be able to forecast at all of these different levels. So we're going to be showcasing a new library, or actually it's not technically new in R, but it was just recently released to CRAN. It's called the LightGBM library, and it's a machine learning algorithm. We're actually going to be focusing on three different kind of similar packages: LightGBM, CatBoost, and XGBoost this week. And we're going to be, again, showcasing the value of learning the Tidymodels framework, which is an ecosystem of libraries. And we're going to see how this ecosystem makes it super easy to do this type of machine learning. Real quick, also, we're going to be focusing, for all you forecasters in the house, we're going to be focusing on the M5 competition, and we're going to be working with a subset of that data today. And it's really cool because we're going to see in just a couple hundred lines of code, we're able to get some really awesome results on it. So very exciting stuff. All right, so with that said, we're going to get started here. Again, this is part 3 in the Tidymodels series. If you missed the first 2 parts, definitely take a look at the Learning Labs Pro program. I'll talk more about that in a second. But the first part was NLP, where we did some analysis that's really important for working with product databases and text fields within those product databases. So we showed how to use product descriptions using NLP, like creating one-hot encoded descriptions and doing all sorts of cool feature engineering with the text recipes package. The part 2 was a couple of weeks ago. That's where we had Max Kuhn on, and he helped us out with a really in-depth customer analytics feature engineering tutorial, and we used the embed package for that. So we did some cool feature engineering using step UMAP and also step, hash, turning the one-hot coded features into hashed features. And then today, what we're going to be talking about is hierarchical forecasting. And then we have upcoming in a couple of weeks, we're going to be doing ensembles too. Also, we also have a special guest too that's going to be not joining us today, but in a few weeks. We're going to be inviting Josh Starmer on once we get into the next series, which is going to be on deep learning. So I'm excited about that. Josh Starmer is from StatQuest. So we will get this thing kicked off. Learning Labs Pro, if you haven't heard of it yet, it's basically, we now have 50 labs, 50 learning labs. And what happens is this recording today is going to be the 50th lab. And we have all sorts of labs that are on in-demand topics, such as marketing analytics, such as working with SQL databases, and so on. These are super valuable labs, and you get a lot of great things like what you're going to see today. So if you like what you see today, definitely sign up for Learning Labs Pro. And David's going to put a link into the chat. The bonus for today. So this slide here depicts the last 3 shiny apps from the last 3 labs that we've done. So 2 labs ago, we did the text recipes. The bonus that our Learning Lab Pro members got was this shiny NLP token automation app. And they got to get that for joining LLPRO. 1 week ago, or 1 lab ago, we had the shiny customer segmentation app, which is where we did the full end-to-end feature engineering for a customer database of 11 tables. We summarized that data and we put it into a shiny app. And then today, what everyone's getting that joins Learning Lab Pro, they're getting the shiny hierarchical forecaster app. So check this out. This is the app. And this is the bonus that we're putting into the Learning Labs Pro program. Here's how it works. So I'm just going to refresh it so you can see if I just open it up fresh, this is what it would look like. And what we can see is we've got a product hierarchy in here. And this is a graph that shows kind of the aggregation from all stores to, you've got 3 different stores, and then each of those stores have multiple stores within them, or each of these states have multiple stores within them. So CA_1 is one of the stores in California. And then you click on that, and that has products that fall into different categories. Those categories go into different departments, and those departments go into different products. So you can see that this long graph kind of shows the hierarchical relationship that's in your data. And what we're going to be doing is talking about forecasting all of this. So from the top level aggregation through the intermediate steps, all the way down to the specific products. And we're going to showcase some of the problems that you can run into when you try and forecast some of this stuff. So right now down here, we have a forecast plot for the next 28 days, and this is for all stores. So this is the top level right here. But what we can do is we can use this drill down to showcase, what different data sets we have in here. So maybe we might want to forecast CA1. So that's one of the stores. I've got CA1 here. I just clicked on that and it's updated. So I've got the test, I've got the forecast here. I've got my test forecast, so I can see how it did on the test data set. I've got the accuracy and everything. And then I can kind of zoom in. If I want to zoom in on it, I can do 6 months or look back 3 months, and you can get a little bit closer snapshot of what's going on. So that is the intermediate step. And that's still not that challenging. But what gets challenging is when you start to forecast some of these down here, they get pretty spotty, and we call that intermittent demand. So let me just check out one of these, foods _3_532. So we'll take a look at that. So when I'm looking at this data, I can see here it's got some spots here where it's 0 right after January 2015, and you can see it kind of gets real spiky. So this is our forecast here, and what we're trying to do is trying to forecast this kind of spotty demand, and that's one of the challenges that you run into when you start to work with hierarchical data. Once you get down to these pieces here, it tends to get pretty spotty. So that's what we're going to be focusing on. This is the bonus that everyone gets today when they join Learning Lab Pro. Also, you get the previous weeks too. I always get this question. If you're interested in getting any of the bonuses for all the labs, definitely sign up, because every lab has a bonus, and it's pretty exciting stuff. All right, cool. The business problem. This is where the rubber hits the road. So we've got hierarchical forecasting that we're talking about with intermittent demand. So the business problem that I already explained with the app is that we've got kind of this hierarchy in our data set. And when we start to roll things up from the bottom level, or when we start to expand them as we go from the higher aggregated level down to the lower level, the data becomes intermittent. And this is can be a challenge for a lot of forecasting algorithms. So here's an example. All stores is where we're at the top level of our data, and that's pretty easy to forecast, because all the seasonality kind of jumps out, and you're able to kind of grab onto that. But then as you start to split it apart, it becomes a little bit more challenging. The series become a little bit more erratic. And then once you get down to the bottom level, you get series that look like this, where you had demand from, we'll say January through October 2015, then there was no demand. So and then you got a spike in 2016, and then it looks like it's picking back up again. So this is the challenge. As you get to the lower level, so this is foods _3_663, which is this one right here, you get these kind of spotty demand. So you want to be able to forecast that, and you actually want to be able to forecast all of this because your business depends on it. The M5 competition. So where does this fit? Well, the M5 competition is one of the first competitions that actually deals with sales data or demand data with this hierarchical structure. So the data set that we're actually working with today is just a small subset of the M5 forecasting data set. We can't use the full data set because it would take hours to train. I saw in some of the submissions that it took between 8 and 12 hours to train on the full data set. Just using a laptop. So we don't want to do that today, but we can still get a good idea. One of the takeaways that I saw was that a lot of the solutions, in fact, I think all 5 of the top 5 solutions use the LightGBM library as part of their winning solution, or as part of their top placing solutions. So LightGBM, was recently released to CRAN. It's made by Microsoft, and it's a really nice library that implements gradient boosting machines, and it's designed for high performance and scalability. So it's a really powerful algorithm to know. But it's actually just one of a couple of different gradient boosting machine libraries that you should know. So we've got LightGBM here in the middle, but there's also XGBoost and CatBoost. So these are all 3 of the primary high performance GBM libraries. You want to get to know these, and we're going to test them all out today. We're going to kick the tires on them, and then we're going to show you how to forecast with all 3 of them. The software that we're using today, I'm actually really excited to do this because my Modeltime package, which is what I teach in my time series course, and this is the package that I spent about a year developing for high performance forecasting. The beauty is when you learn the Tidymodels ecosystem, you now have access to XGBoost, LightGBM, and CatBoost. And this is really cool. So we're going to be using Parsnip, which gives us access to XGBoost, but there's also this new package, Treesnip, that gives us access to LightGBM and CatBoost. So it basically takes these algorithms and formats them so that way Modeltime can forecast with them. It's really sweet, and I'm really excited about it. So this is the software we're going to be using, and if you take one thing away from this lab today, it's Learn Tidymodels. It's super powerful. If you're doing forecasting and if you want to be able to use these algorithms, Learn Tidymodels. It makes it so easy. Okay. We're going to get into the actual learning lab today. So the meat of it is the code. And for my Learning Lab Pro members, I kind of want to take a step back here and just showcase what I've got going on here in this in this project directory. So this is my Lab 50 LightGBM, and you're going to see a couple of folders here. This CatBoost_info. This one's automatically generated by CatBoost, so it stores some of the different logs when you start to use that algorithm. The M5 forecasting accuracy, so this is a subset of the data set that we're going to be working with here, and it's just the sales sample tibble, which comes from M5 accuracy, and then there's also the calendar.csv file. You're going to see this test forecast ensemble, future forecast ensemble, and full data tibble. These are intermediate data sets that I create as I go through the lesson today. And that's where those are. So these are actually generated. So the inputs are going to be the sales sample and the calendar. And then our outputs are going to be these 3 as we go down through our analysis. Okay, so that's the data. This file is the bonus today. So this is the O3 Shiny forecasting app. You hit the run document on this, and it produces our Shiny app. I do have an important note. This app does use the development version of our Markdown. So you need to install this, and you can do that using this sequence of code right here. Just do remotes, install GitHub, RStudio, R Markdown. Okay, and I think those are the big ones. Just make sure that you have R Markdown installed, the development version. Okay, the next in my files, I have O1 and O2. So these are the 2 files that we're going to be working with primarily today. And then the ZZ create data. This is how I created these samples. So it's just a reproducible thing that I kept for my purposes, not necessarily yours. So you don't need to worry about that one too much. But the O1 XGBoost versus LightGBM versus CatBoost, this is where we're going to get started today. And we're going to walk down through, and what this is designed to do is just to give you some exposure to the Treesnip library and to also working with LightGBM and CatBoost. Okay, so we're going to go down through this real quick before I get started. There's two GitHub installations that you'll need to do for this learning lab. So the Treesnip library is not on CRAN yet, so you can't install it with installer.packages quite yet, but all you do is you just run this line of code here, remotes, install GitHub, curso-r Treesnip, and that'll install the Treesnip library. So you need that as a dependency. And then you also need CatBoost. So here's how to install CatBoost. you do DevTools install GitHub CatBoost / CatBoost, subdirectory CatBoost / R package, and that'll install the R version of CatBoost for you. Okay, so once you have these GitHub installations, you're ready to go for the rest, for all the libraries then that we're going to use in the 01 and 02 tutorials. The libraries that we're using today. So the machine learning packages, that comes from LightGBM, CatBoost, and XGBoost. And then the Tidymodels ecosystem. This is not the forecasting section, so it's just Treesnip and Tidymodels that we're going to be using. And then the core package that we're going to also use is the Tidyverse. And I'm just going to go down through and kind of show you a motivating example and some comparisons now with some of these libraries. So I'm going to load 2 data sets. These come from the LightGBM package. There's Agaricus train and then Agaricus test. And we're going to be going down through these. So the training data set is this Agaricus train, and then you make an LGB data set here. So this is what you have to do when you're using LightGBM. And I want to showcase this because this shows you some of the challenges that you're going to have to work with if you don't use the Tidymodels ecosystem. So when I pull in this Agaricus train data set, it looks something like this, and it looks kind of weird. It's got a label here, and then it's got a sparse matrix of class DGC matrix, which is kind of like a special format for storing very large matrices. The problem is that you don't normally work with data in this type of format, and especially not in this detraining format too. So you know, if you're just using LightGBM out of the box, you're going to have to get to know how to convert to these matrices and use this special format. And then it's going to be kind of painful because then you're constantly going to have to be transferring from tables or data frames, which are kind of like Excel spreadsheets, and you're going to have to be constantly converting into matrices, which can only handle numeric data. So you have to like one-hot encode it and all that stuff. And then once you get the data in the right format, then you would run your model. So this is how you would run a training model. It runs. It just did a bunch of you'll see some output here because it just kind of went through its training process, and you can see it did several different iterations, and then you make your predictions here. So the idea here is that this is how you would use that base package, but what happens when you want to use other packages like XGBoost or CatBoost, or what happens when you want to use other different types of algorithms too that aren't in the 3 primary? So say you want to do a linear regression or something like that, you got to completely change your data around. So the benefit of learning the Tidymodels ecosystem is if we convert this data to just a, I need to get that whole thing. If we convert this from a matrix structure to a data frame, which is how I'm most comfortable with working with it when it's in a data frame or a tibble, then I can start to use all of these different algorithms because that Tidymodels system kind of standardizes on the tibble. So what I'm doing here is I'm just converting the training data set and the testing data set from a matrix structure to a tibble structure. And then, so now I have the train and the test. And now what I can do is use the Tidymodels ecosystem to be able to do some training. So just to, because I'm repeating a lot of the code that we're going to see here, I've made some helper functions. One's called train model, one's called make predictions, one's called extract fitted model. They aren't really that important because they're just abstracting away some of the details of Tidymodels. So I'm just going to run these really quickly. And what I want to do is I want to focus on how quickly and easy that we can make these models. So first we're right here. We're going to focus on LightGBM. So I'm making a boosted tree model here. How we do that in Parsnip is we create a boosted tree. And then what Treesnip does is it allows us to use this LightGBM engine. So Parsnip doesn't come with this, but when you load Treesnip, it extends Parsnip and it allows us to add in now the LightGBM package. So when we do that, we can create a specification for a LightGBM model. And then what I'm going to do is I'm going to run this train model, which is just a helper function, kind of runs through this workflow here and fits the data. So I'm going to train the model. We can see it's going through pretty quickly. It's made its training. Now I can make some predictions again with this helper function up here. What I'm doing is making some probability predictions. And then what I can do is assess them using yardstick. And I can see that it gets about a 0.717 right out of the gate. Now, I haven't done any sort of hyperparameter tuning or anything. I'm just literally running the defaults for these models. And, or actually, I did change one of the defaults from learn rate 1 to learn rate 2. But basically what I'm trying to assess is kind of the general performance without a whole lot of tuning, hyperparameter tuning. And this will just give me kind of a baseline assessment for these algorithms. So this one gets a 0.717, and then what I can also do is I can get the feature importance out of that, and I can see which features that it found important in that model, and kind of assess what features, if I'm trying to understand my data better, which ones I should focus in on. So that is kind of how the LightGBM works. And then the XGBoost version of it, what we can do is do kind of the same thing. We create a model specification, and I'm just kind of running it again through this train model function, and then the make predictions function. And I can see that this one's doing really well. I got essentially a perfect accuracy. And then I can also do the plot importance. So I can see that these are the features that this modeling approach found useful. So a couple things real quick. XGBoost may not be the best performing, at least not out of the gate. You might have to do some hyperparameter tuning to improve the model performance. This XGBoost model, though, right out of the gate, for this particular data set, seems to be working pretty well. And also the feature importance. I would trust these features more because the model is doing a much better job at predicting than this model did with the LightGBM. But that's not to say LightGBM is worse than XGBoost. Oftentimes it depends on the data set and the hyperparameter tuning as well. But we also have one more algorithm, which is CatBoost. So we're going to assess CatBoost. We're going to run it through the same process here. And what I'm doing here, the only difference is, let's see, CatBoost, no applicable method for slice. Where did I use slice at? Make sure I grab the right function from dplyr. And these are what the features that XGBoost found important. So these three different packages kind of function very similarly. The AUC, we see this one's getting almost perfect. So CatBoost is also doing very well right out of the gate. No feature tuning, no hyperparameter tuning or anything. And then we can do it with one other data set. So I'm going to actually do a slightly different approach here. We're going to use the diamonds data set, and this is for a regression problem. I'm going to set a seed, and I'm actually going to do some splitting of this. I'm going to do not cross-validation, although I'm using this vfold CV, which stands for cross-validation. But basically, I'm using this as a sampling procedure, and I'm going to be repetitively training and seeing what the average accuracy is for this regression task. So we're going to run through kind of a similar type of process. I'm actually going to run these in parallel. And what this will do is it'll speed up the computations a little bit. And then, it doesn't look like for some reason it's running in parallel. But it finished pretty quickly, so not to worry. Let's run this one. Okay, this one looks like it is running in parallel. So when you see this output here, that means it's not running in parallel. When you don't see the output, that means it's typically running in parallel because I have verbose equals true. And it should be finishing up here right directly. So I'm running the LightGBM now. It's finished, and I'm doing the same thing for CatBoost right now. And we're going to compare the resamples here. And what I'm showcasing here is that this is a different type of problem. It's regression. It's with a different data set, and we should see some different results. So this one here, lower is better for the RMSE. And this one, XGBoost, is winning the second set, the second test. And we can see after 5 iterations, this one has 557 for the RMSE, which is a ton better than LightGBM and way better than CatBoost. So different data set, different problem. We can see that XGBoost is doing pretty good with this one, whereas the last problem, it looked like CatBoost and XGBoost were doing the best. And this one, LightGBM, is kind of in the middle. Again, this is just with the defaults. I haven't done any hyperparameter tuning, but some conclusions here. Hopefully this shows you kind of the value of trying all 3 of these different algorithms. So one of my conclusions here, the algorithms can vary significantly out of the box. Experimentation with multiple algorithms is quite often very important. And what I like to do is I tend to focus on which ones are performing the best without doing a whole lot of hyperparameter tuning, because that's where I'm going to be best dedicating my time. Okay, so that was just to expose you to a little bit of XGBoost and LightGBM and CatBoost. Those are the algorithms that we're going to be working with today. Now we can get into the forecast tutorial. So you've kind of seen and been exposed to these different algorithms. Now what I want to show you is how would we use these to actually forecast and do a high performance forecast. So we're going to be doing hierarchical forecasting with LightGBM and friends. The business objective today is to forecast intermittent demand and to predict the next 28 days worth of timestamps, okay? So GitHub installations, again, the same thing. We need to have Treesnip installed, and we need to have CatBoost installed. So those are not available on CRAN. You're gonna have to install them from GitHub until they're released to CRAN. I don't know when that will be. The libraries that we need, we're gonna need our machine learning libraries. So LightGBM, CatBoost, and XGBoost. We're gonna load these 3 libraries. We're gonna load Tidymodels again. So we're doing Treesnip. This time we're doing Modeltime and Modeltime ENSEMBLE. These are my 2 libraries for forecasting within the Tidymodels ecosystem. And we're also going to be using the Tidymodels set of packages as well. And then we're going to load Skimmer, TimeTK, and the Tidyverse. Okay. All right. So once we do that, we're ready to pull in some of the data sets. So the data sets that we're going to be pulling in is in the M5 forecasting accuracy. It's going to be this calendar tibble, which comes from this calendar.csv. So this data set here looks something like this, where we've got date. It's got some date features in there. We aren't really going to use those. What we're really interested in is having the timestamp and this D, which links it to the value from the forecast. Now the sales sample is the next data set, and this is a sample of the M5 competition data. It's not the full data set, but it's a sample of the sales data for 50 of the products. So the reason I'm doing this, I'm doing a sample of them, is because it would take a long time to do the machine learning for their full database, which had, I think, something like 50,000 products or so. So we don't want to do that. So I pulled in the data set, and it looks something like this. If you've never seen this type of data before, the days go across the columns, and this is what is called a columnar data set. A lot of kind of high performance databases that have to handle lots and lots of data, they store dates in this kind of format where the columns are the actual dates. And that allows them to select them very quickly. But the important information is actually right here. The ID, the item ID, department ID, category ID, store ID, and state ID. And then these are each of the different days from D1 all the way up to, I think the last one is like 700 or so. So it's like, it's 1900, 50 by 1,947. So it's 1,947 columns in this data. So the way that this D1 works is that links up to over here. This is day 1, and then you can get the timestamp. Okay. So we're going to have to combine these 2 data sets when we do our forecasting. And then what I'm doing is I'm actually taking that sales sample and I'm selecting all the columns that contain ID, and I'm storing that as something called hierarchy tibble, because this is the hierarchical information. This is the thing that relates like one time series to another. Okay. And then what I'm going to do is I'm going to take my sales sample, which is, again, it's only 50 rows, but I have to convert it kind of into a time series format that we can analyze. So I have to pivot it to longer. And what I'm doing is I'm taking all of these rows here and all of these columns, and I'm going to kind of pivot them and reshape it and to get it into a kind of a columnar format or a row-wise format. So this makes 97,000 by 8. And you can see day now goes D1, 2, 3, and so on. And then what I'm going to do is I'm going to pull in the timestamp next from the calendar features. And then once I do that, I've got the date here, and I don't need any of this other stuff. These are more features, but I don't know those going into the future. Or I do know the weekday, but I'll do some feature engineering to pull out timestamp features later. So I just need that date. So I'm going to select anything that contains ID and then the date, the date and the value column. Okay, and that's what's going to be my sales sample long, and that's going to be the start of my analysis. So I've got my data kind of merged. Now I'm ready to start doing my analysis. From an exploratory data analysis perspective and a data cleanliness perspective, I can't tell you how often I use this package called Skim. So basically what I do is I run through my data next, and I want to make sure that I want to identify any issues that there might be with it. So I'm looking at how many each feature here. So it's got the variable types. It splits them into character, date, numeric. And I can see I've got a 100% completion rate, which is good. Number of unique values. So there's 50 unique items. There's 7 unique departments, three unique categories, 10 unique stores, 3 different states that we're going to be working with. And I can see the date feature if there's any missing. Now there's a little bit more exploratory information that we need for our date feature to make sure that it's padded, and I'll go through the feature engineering on this. And then there's the numeric value. So this is our target, and this is what we want to try and predict. This is our value. Again, it's got a 100% completion rate, and it shows you kind of the average and standard deviation, that sort of thing. But basically, I want to know, am I missing any data? And if I do, I need to correct that data. So it looks like we aren't missing any data. So far, so good. Next, what I'm going to do is I'm just going to do a quick visualization. I'm going to take, so we have 50 different time series. So you can see that by this item ID, there's 50 unique values. If I try to make a visualization with 50 values, it's going to be pretty hard to understand. So I'm going to sample that down, and I'm just going to grab 6 of those. And these are the random 6 that I'm going to grab. These are the item IDs. And I'm going to then plot those using plot time series. What just happened there? Oh, I have R Markdown running. I need to stop that for a second. Okay, so let me run this. And we should get a visualization over here. And you can see what we're dealing with. So we've got 6 random samples of the 50 different time series that I have that I pulled. And you can see the types of issues that we're going to be running into. We got intermittent demand, very spotty, very granular, and so on. I've added a smoother here to kind of tease out to see if there's any seasonalities in here that might be worth trying to grab onto for doing our machine learning and so on. So it's going to be kind of a challenging data set to predict, but it's going to be a fun one. So the first thing that we do, and I teach this in my time series course, we have to do some feature engineering, and we have to do, and we basically have to format this in the right way to be able to do some forecasting with it. So I call this making a full data set. And what that full data set does is it contains both the data that we're going to be modeling with, and then we're also going to use and extend this data set into the future. And that's going to create a frame for us to do the future forecast with, because our future forecast is going to need all of the different engineered features, and it has to be filled out in that. So I'll explain more about that in a second. But what we do is we start with our sales sample long tibble, and this is 97,000 by 7. And you can see in here, it's got the item ID, which each one of these item IDs is our time series that we're going to be trying to forecast. Now, there is a strategy here, and there's a couple of ways we can attack this problem. Because what we want to do is also forecast some of the aggregations. The way that I'm going to do that is I'm actually going to create aggregations within this data frame. So I'm going to add a column called all stores. So that's another column here. And basically it's saying everything belongs to all stores. So it's only one unique value, all stores, that gets propagated 97,000 times. And then what we're going to do is we're going to do some pivoting, and we're going to reshape this so I can get the values for each of these different all stores ID, item ID, department ID, and so on. So this is a reshaping operation. It can be an expensive process if you have a lot of data, because it just converted into 58,000 rows. But this is one way we can attack the aggregation problem. And we're actually going to forecast the aggregates. So what I'm going to do is then I'm going to summarize the data, because I've got now a column called category that has all of these different categories and then the identifier that's associated with it. So these categories were the columns that we had, these columns right here. They just got shifted into a category column, and then it has an identifier that's associated with it. So I can use these as grouping variables to group by category, identifier, and date. And then what I can do is do a summarization of this value column. And when I do that, I now have aggregates in here. So I have the aggregated value of all of the stores. And I can see when I add all of those up for this particular date, and so on, I now have the aggregates in here. So this is creating a forecastable data set where I don't need to do any additional math to be able to produce a forecast. I have all of the different combinations that I'm interested in also in here now. So all stores is the top level of the forecast. I also have the state level aggregations in here. I have the stores within those states, and so on. Okay, so once I aggregate it, then what I'm going to do is I'm going to start doing my time series operations. So I'm going to group by category and identifier, and then so it's going to leave date and value ungrouped. And then what I'm going to do is I'm going to start fixing time series. So I'm going to use the pad by time first. And what that's going to do is add in any missing values. I don't think there are any missing values. And when I say missing values, I mean missing timestamps, but this will correct it if there are. I'm also going to extend each one of these series 28 days into the future. So that way we can begin to forecast, like that's going to create the forecastable data. And then we're going to add some lags and do some sliding operations and so on to get some rolling averages. So when I do that, when I do all of these, this whole feature engineering pipeline, what this does is it creates what's called the full data set. And this contains both the future data that I want to forecast and also the training data that I'm going to be using to produce that forecast. So let's take a look at what this full data set looks like. Okay, so I can see that I've got now, instead of just category, identifier, date, and value, I now have some extra features in here. So I have the value at lag 28. I have a rolling average at 7, 14, 28, and 56 periods. And that's what these columns are here, where you see the roll in there. And what those are going to be is engineered features that we use for doing our predictions. I can also skim this data, and I can see kind of different things that I'm interested in, like how many missing data points, how many total rows, and so on. One of the things that I see here is that there's a lot of missing data and value now. And the reason that we have that missing data is because I extended each series forward by 28 days. So 28 times 50 is 1,400, and there must be some other something else going on in here on the value end that's creating 2,072 observations here that are missing. The value lag 28 also has the same amount of missing data, and so on. So and then there's the rolling that are going to have some missing data as well. So what I want to do is I'm going to do next. So this line here saves this intermediate data, and then what it does is it reads that data back in. So there's one other thing too, that if you're interested in hierarchical forecasting, you're probably going to say, well, hey, you don't have any hierarchical forecasted features in here. So if you look at our full data again, and let me do a glimpse of it. Let me run this one. So what glimpse does is it allows me to see all the different columns kind of like stacked on top, and it's good when your data sets gets really wide to if you're trying to review it. So you're going to see in here that, like, for example, category all stores. So that's the first data, that's the first time series that I have in here. You're going to say, okay, well, shouldn't you have columns in here for like states and things like that? We can add in those, and what those are called are hierarchical features. And what it does is, if we want to do that, what you normally do is you do it at the lowest level, which is your product level. And that's what I can do here. I can take my full data set and do a left join on my hierarchy. So that's this here. These are the hierarchical. So what I would do is do a left join by this item ID. And for anywhere that this item ID pops up in this identifier, I would pull in that data. So I did this, and the funny thing is, so you add in, let me do a glimpse here. So what this will do is it will add in columns that of the hierarchical features: department ID, cat ID, store ID, and so on. Now you're going to see it here, and that's because all stores is an aggregated feature, or an aggregated time series, and it's the sum of a bunch of different the sum of specific products all rolled up through that chain. The problem is that you're going to end up forecasting and using these features, and we can do that, but I tried it, and it actually didn't improve my model very much. And so I started asking myself, well, why didn't it improve my model? Because I thought, when you do hierarchical forecasting, that you actually need to have kind of the relationships built in as additional columns, because that's kind of how I've done it in the past. And I started thinking about it, and it's because it's most likely because the tree-based models are naturally hierarchical. Because when you model with XGBoost or with something else like LightGBM, they're able to kind of cluster and kind of group the different features based on this category here. So if it belongs to certain categories, it's able to kind of create models and kind of group those models together. And that's what it does when it makes its tree-based structure. So what my thought process is this algorithm actually most likely groups similar products together, or most likely groups similar locations naturally together. So by including these types of features here, we don't actually need these features here, if that makes any sense. But so that's the way I kind of justified it in my head. Whether or not it actually plays out that way, I'm not sure. But that was just kind of one way of me kind of justifying it to myself, that I didn't actually need these features in order to be able to get decent model performance. The other thing is there are other alternatives to this approach that I'm taking in here. One is we can model just the lowest level and simply add aggregates together to kind of roll things up, and that's a good strategy as well. The problem is that when you go to make an app, you're constantly going to have to figure out, what products need to be rolled up together in order to get to the top level. So my solution is in an app, you can just forecast the different combinations that you want to have available. And if you know them in advance, you can forecast those. And then a second alternative that I saw with some of when I did the review of the M5 competition was you can create two different modeling strategies: an aggregation strategy and a product level strategy, and then model each separately. So that was another alternative that you can explore. So I'm actually not going to include these in because it's going to adding more features costs you more resources, and it makes things take a little bit longer to run. So now what I'm going to do is I'm going to take that full data set and I'm going to split it up into data prepared. And then what data prepared is anywhere that there was a missing value in the value column, it's going to get rid of those. So we don't want any of the missing values. And the reason a missing value happens is because that's part of your future data. So that's what you're going to be trying to forecast. So we're actually kind of, if you're visualizing it, you're taking your full data set and you're splitting it off into a data prepared, and you're splitting it off into another data set called future data. So I teach this in my time series course. The future data you will see has value missing, and it's all of the timestamps that we want to forecast into the future. So starting at the last day, which will be the end of, so we're seeing 2016, 05, 22. So 05, 23 is the next day. So this is what we're going to try and forecast. And the good thing is that you want to see all of these features that are completely filled in. So because these are my engineered features, these are things that that machine learning model is going to need to have filled in order to be able to forecast these values here. Okay. All right. So once I have my data prepared and my future data ready, I'm going to be kind of set the future data aside until we start to do my final forecast. And what I want to do is I want to start working on this data prepared now. And this is what I'm going to be training some models and testing on. So I'm going to make some time series splits. And what this is going to do is it's going to take my data prepared, which is a big time series with overlapping timestamps for all of these different stores in here. And then what I'm going to do is create a time series kind of test plan. So what it's doing is making a visualization here. And we can see that most of it is blue. So this is all the training data is blue. And then this last data set here is red. And if I zoom in on this, I can see that there's that the last 28 days are what's going to be in my test data set. The next thing I'm going to do is I'm going to start working on this blue data set. I'm going to create a pre-processing recipe. So we've got this training data. So if I take my splits object that I just split up here, and I take a look at the training data set, looks something like this, I need to do a little bit of work on this. So a machine learning model is not going to be too excited about getting a date feature in it. I also, this row ID, we don't need that. And I want to take this date feature and convert it into machine learning type of, I want to pull out features from this timestamp, so feature engineer it. So I'm going to run it through a recipe. First, I'm going to change the role from row ID and date to a role of ID. So these aren't used in my machine learning model. Next, what I'm going to do is use this step called step time series signature and apply that to the date column. And then I'm going to remove features that get added in here that are not needed for the model. And then I'm going to dummy all of the categorical data. So anything like this identifier in here, that's going to get dummied and so on. So when I create this recipe here, what it does, we can see kind of the recipe summary. This is on the incoming data. I can see that it has now changed the row ID and the date to ID, which are the roles there. So they're no longer predictors. These are all of the predictors, and then the outcome is value, so that looks good. And then if I can actually run this same thing again after I prep it to see what how many features would be created and what their roles are. So I can see now it's 123. These are the ID features. These are predictors. This is the outcome. And I can see there's now 123 columns in there. And then I can get a look at the actual transformation if I run recipe spec prep juice and then glimpse. It takes a second to process, and I can see here that it's a lot of columns in here. And most of these columns are now ready for machine learning algorithms. So we don't have any character data or categorical data in here. It's all zeros and ones, or it's all numeric values. You still see the date in here in the row ID, but if you look up here, these roles are IDs. So they're not going to be used for the machine learning models. Okay. So that is the recipe. Now we're ready to start doing some machine learning. First, we're going to tackle the LightGBM. So I'm going to create a workflow. This is a blank workflow, and this is part of the Tidymodels ecosystem. So you can see that there's no preprocessor or model. I'm going to add in a LightGBM model. I add that in, and then I'm going to do the add in my recipe, and then I'm going to fit it to the training data set. So this takes a second to run. It's a fair amount of data. It's like 150,000 columns, and you can see that it's running, and there it's now just finished. Okay, so it's one of the nice things about LightGBM. It's fast, and you can do, this is what makes tuning them a little bit more pleasurable than some of the other modeling algorithms out there, is that they do run so fast. So you can imagine having to tune this 10, 20 times to figure out which hyperparameter combinations work the best. Makes it a little bit easier if you're using a faster algorithm. One of the things that they did in the M5 competition is they actually used a different objective function. So this is how you can change the objective for the LightGBM model. So if you work on this set engine where it says LightGBM, LightGBM, so anything else that you add in here, any additional arguments, these get passed to the lower level functions. And so this objective equals Tweedy will get passed to the LightGBM training function. And what this does is it changes the way the distribution loss function. So that way, when you're working with intermittent demand, the Tweedy objective versus just your normal, like whatever the default is for the LightGBM, it's probably just like some sort of RMSE objective or something like that. The Tweedy objective will tend to do a little bit better when your data has a lot of zeros and ones. So this is something that they did in the forecasting competition, the M5, and it's something that we're going to try out as well. So that's the only change here to the second one. So there's a workflow LightGBM defaults, and then workflow LightGBM Tweedy. Okay. The nice thing is once you get the Tidymodel system down, you just basically keep replicating this for each of your different models. So we're going to do the same thing with XGBoost, one with the defaults. We're doing that right here. And then we're going to do the same thing with Tweedy. So I had to look up the documentation for XGBoost. XGBoost does have an objective Tweedy. You just pass it reg::Tweedy. So we're going to run this next. I did notice XGBoost does take a little bit longer to train than LightGBM. But it's just kind of the function of the algorithm. Okay, next we're going to do CatBoost. So it's basically the same process, and this is the advantage of using Treesnip package is we can now just swap out set engine from LightGBM to CatBoost, and we can do the same type of analysis or build a model for a CatBoost. So this is the one with the defaults, and then the way you do Tweedy for the CatBoost, I had to look up the how you pass that. There's a loss function parameter, and you set that to Tweedy with variance power equal to 1.5. So when we run that, we get the CatBoost Tweedy. Okay, so now we have 1, 2, 3, 4, 5, 6 different models. And how would we want to forecast? Well, that's where Modeltime takes over. So once you have all of your models created, and you would already do your hyperparameter tuning and whatever else, but once you're pretty happy with it, the idea here is you can take it into the Modeltime workflow. And what this does is it helps out with actually doing your forecasting and actually comparing and selecting your models. So that's why you use Modeltime. Here, what we can see is we made a Modeltime table, and we have our 6 different models in here, and it has an ID to them and a description to them. So what I'm going to do next is I'm going to calibrate them, which means what we do is we basically do a forecast on the testing data set. It gets stored as data in here as a new column called calibration data. You can see it's 2072 by 4. And what that's doing is it's basically calculated what the prediction was and compared it to what the actual data set was. So you've got now an error estimate. So that's what calibration does. Also here, this next line of code, all we're doing is we're going to change up this model description here and add in Tweety for these last three. So I'm going to store that as my calibration tibble. And once I have my calibration, I can start to do fun stuff like getting accuracies on them. So if I do get the accuracy, I can see XGBoost is doing pretty well here. This XGBoost Tweety is doing pretty well. And then I can see that the R-squareds are doing fairly well for XGBoost as well. CatBoost seems to be in the second place. So CatBoost, just a regular CatBoost without Tweety is doing pretty well from an R-squared standpoint. From a MAE or an RMSE standpoint, definitely the XGBoost model is doing the best. LightGBM looks like it's probably in second place for RMSE. But what we need to do, and what is often good, is we want to assess it by time series, because what happens with time series is the aggregated values can really throw off. So basically, like as long as your algorithm does good on an aggregated value, these metrics are going to look better or worse depending on how it does. So you want to really actually look at the sub level and like each time series individually. We'll focus on that here in a second. So the next thing that we want to do is we want to forecast on the test data set. So we take our calibration tibble, and basically what this is going to do is it's going to predict it on this red region here. So we're going to forecast our new data as our testing splits. Our actual data is data prepared, and we're going to keep the original data in there. And I'm going to save this as test forecast. So this produces a tibble. So it takes this calibration tibble, forecasts each of the models with it, and it produces the predictions. So those predictions are present here in a dot value column. It also gives you a confidence interval as well. Now notice that actual values, so this blue, you're going to have missing values for the confidence interval because that's not a prediction. Okay, next thing that we're going to do is we're going to visualize. So we want to visualize the prediction on our test data set. We can create some visualization filters because we've got a lot of data in here, 150,000 rows. So in order to be able to visualize that, I'm just going to first focus on all stores. I want to see how the algorithms did on all stores. So I'm going to run this line on 265, and then I'm going to come down here to the visualization script I have, and I'm going to filter that data down just to all stores. So now this data set is only 2,000 rows. A lot easier to visualize 2,000 rows. And then I'm just going to run these. This piece here, so I'm grouping by identifier, and it's going to allow me to compare all of these different algorithms. You'll notice that I have this filter by time in here. And what I'm doing is I'm using this to kind of hone in and zoom in on this last segment here. If I didn't include this script here, and if I run this, what I would have to do then each time I did this, I can barely see this over here, and I don't want to miss something. And it's kind of tough to zoom in on that particular piece of it. So in order to zoom in, I'm using this filter by time function. Okay, so what I can see here is that for that aggregated, so this is if you think the top level, I can see that the XGBoost, the green one's doing pretty good. And then if I highlight the blue one, this is the Tweety version. Tweety's also doing pretty good. I can see here that the LightGBM and the LightGBM and the CatBoost not doing so hot. So this tells me, this kind of confirms to me some of the things that I saw here when I checked out the accuracy, is that the XGBoost seems to be doing a pretty decent job, at least right out of the box. Again, we did not do any hyperparameter tuning. And that's just kind of, we're examining the right out of the box performance. Next thing I want to do, I want to take a look at the state level forecast. So I'm going to filter my identifiers now. So instead of having all stores, we've got the state level identifiers, which are going to be California, Texas, and Wisconsin. And what we're going to do is I'm going to change this over here from identifiers all to identifiers state. And what this is going to do is it's going to filter now my test forecast just to the 6,000 rows that correspond to each of the different states. So California, Wisconsin, and so on. So I'm going to run the same code again. And we can then again inspect the forecast. So again, I'm seeing that the blue models and the green models are doing fairly decent. And these are the XGBoost models. I'm also seeing that out of the box, LightGBM and CatBoost aren't doing so hot. And then I can do the same thing now. So we took a look at the state level forecast. Now I want to look at the item level forecast. So what I'm doing is I'm grabbing the items that we looked at previously, foods, household, like these are actual individual products. And I'm just going to poke that in here. And I'm going to change this to filter identifiers items. And these are those 6 products. So again, when I zoom in here, it looks like XGBoost is doing the best for most of these time series. So this is all data that the blue data that that algorithm has not seen yet when I did the training on it. And XGBoost seems to be winning the battle here. Okay, now I previously told you that what we're interested in is not just the high level aggregated accuracy of everything, but we actually want to look at each time series separately. So this script here calculates the accuracy by identifier. So I'm going to take my test forecast, and I'm going to do a bunch of manipulation, and basically what it's going to pop out is the accuracy for each of the different models by identifier. So all stores, foods, etc. And we see there's 444 different identifiers. And then what I want to do is I want to filter which one did the best. So I'm going to focus in on RMSE, and I'm going to take a slice. I'm going to group by identifier, and I'm just going to grab the lowest value RMSE, which row had the lowest, and then I'm going to take a look and see which algorithm had the best. So when I do that, it just grabs the, I believe it's 74 best algorithms, because there's 74 different features. There's 74 different time series in here. 50 are the products, and then the rest are aggregates. And then what I want to do is I want to see, first we can view them. So if I view it over here, I can see, which, for all stores, XGBoost had the best. For California, XGBoost. So it's basically a scoring for each of these algorithms. And I see here CatBoost had the best on this one, and if I wanted to check that one out, I could look at that. And I can see CatBoost and LightGBM are in here a couple of times. But what I want to do is I can just count the number of appearances that they're the best. So this tells me everything. I see XGBoost is the best 35 times. Tweety XGBoost variant is the best 31 times. And then I can see CatBoost is only the best, a handful of times, and then LightGBM is only the best once. So again, and I keep saying this, I did not hyperparameter tune. So that's probably why we're seeing such a lopsided win here. But for this particular problem, we at least know that XGBoost is doing pretty decent. The next thing that we'd want to do is we've got 2 models in here that are doing pretty good. So what you want to do is you want to ensemble them. One way we can ensemble them is we can take our calibration table, we can filter just to those 2 models, and then we can use this function that comes from the Modeltime ensemble package, and we can provide some sort of loadings in order to be able to kind of instruct on how to combine them. So I'm using a loading of 2 to 3 ratio. So the majority actually will go to the Tweety, but you can decide whatever loadings you want to use, and then we'll put that into a Modeltime table. So this is actually instructions to produce an ensemble and aggregate and combine those 2 different those 2 different XGBoost models. Okay, we're going to save that as ensemble table, and it's just a Modeltime table with an ensemble model in there, and I can see it's got 2 models in there. That's what that ensemble is using. We'll just kind of run through the same process again. We can create a test forecast ensemble, and this is on our testing data set. So we could get things like accuracy and figure out how it's doing. We could also visualize it. But I'm going to skip that part and I'm going to jump into refitting, because when we go to make our future forecasts, what we normally want to do is we want to refit on the entire data prepared. So we split this data prepared up into a training and a test set, and that's what we've been doing all of our accuracy calculations on. But now what we want to do is we want to get ready to do our future forecasts. So we're going to refit, use this Modeltime refit function, and we're going to take our ensemble now, and we're going to refit it. So I'm going to run this. It takes a second to run because if we remember, XGBoost was actually the slowest of the, not super slow, but it definitely wasn't the fastest algorithm. So it takes a second, and it's got to run that twice on the full data set in order to be able to refit those models. Once it's done, it should wrap up here in a second. We'll create this future forecast ensemble. And this is going to be the future forecast, the predictions data. And this is what we're going to want to visualize. And this is what your company is going to be interested in. Okay, should be wrapping up. Crossing my fingers, here's a few seconds. And we're done. Okay, cool. So once we have our future forecast ensemble tibble, it looks something like this. This is all of the data. It's got our values in here of our actuals, and it's also got the forecasted value. What we can do is we can filter in and start to look at different items. So if I just filter by identifiers items, these are the 6 items that I wanted to check out at the lowest level. We can see what that future forecast looks like. And it looks like it's doing a pretty decent job, especially given that some of these are kind of spotty. We can then swap this out and do, instead of the items, we can go to the middle level. So we can do state. And we've got the state forecast here. Again, it looks like it's doing a pretty decent job. It's kind of getting the ebb and flow. It looks like it's getting the upward trend of these two. And then if we do the final kind of gut check is all items. And this is the total aggregate. And it looks like it's doing a pretty decent job on this one too. So it gives me good confidence that we've got a decent model here that's going to help us be able to predict this very tough challenge. So we now have a forecast ready, right? So let's just kind of recap what we've done here. We had a hierarchical forecasting, which is a challenging problem. It's a lot of data. It's tough to manage it. It's tough to kind of streamline it. And you're probably thinking, holy crap, Matt, you just went through a pretty crazy tutorial here. It's like almost 400 lines of code, and there's a lot to forecasting. I didn't realize it was going to be that in depth. Well, you're right. But here's the key. This is only 380 lines of code. You should see how many lines of code the winning solutions of the M5 competition were. They were probably 10x, 20x this. So this is actually an improvement. We came through this problem, which is a tough kind of challenge of hierarchical forecasting, and we came through it in actually quite a few lines of code. I mean, it wasn't very much lines of code. XGBoost was the winner for our data set, but I can't emphasize this enough. Experimentation is super critical. So we tried out XGBoost, we tried out CatBoost, we also tried out LightGBM. Reasons that XGBoost may be the winner here, I didn't do any hyperparameter tuning. So that could probably be one of the reasons that CatBoost and LightGBM aren't performing as well. So if we did some sort of hyperparameter tuning, we probably would get better. The other thing is I didn't go over anything about like more sophisticated ensembling approaches. You know, there is a lot to forecasting, and this is just kind of a straightforward approach. I also didn't go through deep learning. So if you're interested in learning these more in depth and actually learning how to do this entire process that I went through here in a structured manner, then I definitely cannot recommend enough my high performance time series course, DS4B 203-R. We'll be talking about it here in a minute, but that will teach you everything from feature engineering to how to work with time series to how to do machine learning and how to do deep learning with my Modeltime Gluon TS package. So very powerful stuff. This is basically what most companies need. Is to be able to do this type of hierarchical forecasting. And if you learn this in depth, you're going to be a super valuable asset to that company. The other thing too, check out Learning Labs Pro, the hierarchical forecasting app. So we all of my pro members are getting this as a free resource for being a member of Learning Labs Pro. It's the bonus today. Each lab that I've done in the series has gotten a Shiny app to it, and you can get all of those Shinies app when you join Learning Lab Pro. If I click the run document, basically what this does is it packages up our analysis in a user-friendly way that other people can digest it. So if you think about it, the code that we went through in 02, that was pretty complex. People aren't going to have R or Python on their computers at work, but what they will have is access to the internet. So if you put your analysis into an app that looks like this, where they can click on things and drill into them, and then you teach them how to look up things. So if you want to look up foods, you just type in foods here, and it produces the forecast then for foods. You've got your test forecast. You can see how the model did on the test data set. You can see the test accuracy and everything here. If they want to look at specific items, hey, they had some manufacturing told them that messaged them and said they had a stock outage of foods 3532. So you better look into that one. Foods. So if I do foods underscore 3_532, we can check that one out and see what's going on. Okay. Doesn't look like they should have had a stock outage. We're forecasting pretty good. So you get this app, and that's a pretty big bonus here. Okay. So that is the training for the hierarchical forecasting. I know there's a lot to it, and I think that most of you guys, when you're trying to figure out, how to do some of these more complex topics, it can be a lot. So the question that comes to my mind is, how do I learn what we just did? Matt just talked a lot. You can see the power in it. We got a really good forecast. We basically replicated the M5 competition in 380 lines of code. So how can you do this for your business? You need to learn what I just did. So my goal is to accelerate your transformation. What we just saw was pretty advanced, and it's definitely on the advanced end. If you look at a scale of where we all start, which is over here, to what we want to become, which is over here. So my goal was to get you to be the motocross rider right here. And, don't feel bashful. I mean, I know I was definitely in this camp over here when I first started. So I want to get you to become a motocross rider, and I want you to graduate from riding the moped. So that's what happens with business science. And I'm going to talk a little bit about my program now for those that are interested. So the key question is, do you know the tidyverse already? And answer that honestly. Have you worked with R before? Have you done time series before? Have you done certain things before? If you know the basics about the tidyverse, then maybe the Learning Labs Pro product is for you. And David, if you want to put that link into the chat now. So who is Learning Labs Pro for? So what you just saw today is it's on the advanced end. I mean, we're definitely talking some advanced stuff, hierarchical forecasting. So what LLPRO does is it teaches lots of important topics that help you keep learning beyond just the basics of data science. So if you know the tidyverse, which is kind of like, level 1 as a data scientist, and you got to learn the tidyverse. If you graduated beyond that level, then maybe Learning Labs Pro is for you. And you can see some of the topics, check out the topics. If they interest you, then maybe Learning Labs Pro will help you. So we're right now on this Tidymodels extension. We've done text recipes, embed. We just did Treesnip. We're going to be moving on to stacks and ensembling soon. We've got Torch coming up. Josh Starmer, CEO of StatQuest, he's going to be joining me for some deep learning training. We've got other things coming up as well, like big data, Bayesian, targets, simulation, more time series topics that are kind of on the advanced end, and applications that are on the advanced end, like marketing analytics, HR analytics. So if that interests you, then definitely check out Learning Labs Pro. But what if I'm interested in learning R and Shiny much deeper, and I'm just kind of starting out? Well, that's what the R track is for. So the prerequisites for Learning Lab Pro, you definitely need to know the tidyverse. So we're talking about stuff that's over here. If this feels uncomfortable to you, you got to check out the R track, and I'm going to talk about that now. So, say you're kind of like most data scientists. You probably tried several different programs that are out there. And what if this is you? I've already tried everything. Why is your program different? This is the question that would come to my mind if I was in your shoes, and I'm listening to Matt, who, I don't really know that well, but he seems like a nice guy. And, the idea here is that we're different. And I know everyone says that, but why are we different? Well, the first thing is my program is integrated. It was made by one person, me, and it was not kind of farmed out to a bunch of different people that never communicated, and then it just kind of put it into something called an R track. I designed this program specifically to help you grow step by step by what's called breaking through learning plateaus. So what happens when you train in data science is you start learning something really fast, and it feels exciting, and you're really happy with your progress. And then after week 2, your progress starts to slow. And what ends up happening to a lot of data scientists is months start to go by and by and by, and you've never progressed through that plateau. So the program that I designed breaks you through those learning plateaus. So the first one is the business analysis with R. That gets you through that first learning plateau. That gets you the basics of data science. That teaches you the tidyverse, and it teaches you all the important skills that I call 80-20 tools. These are the tools that I use every day, the 20% of tools that get 80% of the results. So that's what this course does. And then what happens is you start to graduate. You then get to the next level. So you're going to start learning advanced machine learning, time series. You're starting to learn Modeltime. You're starting to learn these new tools that really accelerate your development even further. So you kind of plateaued, and then now you're on a new high. You're learning something even new that is going to be super valuable to your company. And what happens is you learn that over the next period of time. And then what happens? Okay, you start to plateau. How do we keep breaking you through? We break you through the final barrier, which is web applications. This is how you distribute your work to non-technical people. So developing that application that I showed you, the hierarchical forecaster, that was developed with a technology called Shiny, and that's what I teach here. So I have 2 courses on that. So this is what the 5-course R-Track system, that's how I designed it. It's to break you through these learning plateaus. What ends up happening is, instead of you taking 12 months and realizing, hey, I haven't really progressed that much, and I still am having a tough time applying it to my work, within like 3 months, within 6 months, you've gone from beginner to expert. Within that first week, you're already applying things to your work. So that's what the system does. That's how it's integrated. 2, how can I prove this? Well, it gets results. So if I look at some of my students, basically they're doing some amazing things. This is Jennifer. She did an awesome job. She actually utilized some of the tools and techniques that I taught her in her job interview process. She followed this thing called the business science process, or the problem framework, and she used our markdown in order to be able to get fast-tracked an offer from and land her dream job with the VP Strategic Analytics with one of the JP Morgan's companies. So, the stuff works, and it's not just her. I've got now a laundry list of students that are doing amazing things. So we've got Masataki, we've got Zidu, we've got Mohana, Herb, Raj. Each of these students has done amazing things, from getting jobs to getting promotions to getting raises to building apps within the first 3 months to winning the 2020 Shiny competition. These people are learning a lot through the program, and that's the common thread. So what I want to do is I want to extend an offer to you. If that sounds like you, if you've been using all these other products and you've been bouncing back and forth between all these other learning platforms, then maybe you should give business science a try. And the thing is, we're going to do things a little bit differently. You're going to learn at a rapid pace, and it's going to push you. But the stuff is, I'm not going to say it's easy to learn, but if you do the work and you put in, 5 to 10 hours a week into your studies, within 6 months, you're going to be in a completely different spot, possibly getting a new job, possibly getting a raise, possibly definitely feeling more fulfilled and excited about applying these new technologies and software to your job. So that's what I'm excited to do. I love doing it. I love helping you. And this is the program that'll help you do it. All right. With that said, I know we went through a lot in this tutorial today. I'm ready to answer questions. If we still have people hanging around that have a lot of questions, I'd love to handle them.
Sure. So just really quick, I put the link to the courses in the chat for anyone who might have missed it. There's been quite often with machine learning and modeling, there's lots of questions around the different algorithms. But I think one thing that you said, Matt, that stuck out was the importance of testing different algorithms. So maybe you could talk about that a little bit. How does that work within the workflow of modeling?
So experimentation is super important. And that's one of the reasons that I designed Modeltime. It's because the challenge is that you need to try many different features. You also need to try many different algorithms in order to be able to kind of see which ones are going to work the best. And they may not always work the best with different feature sets. So you need to be able to come through that pretty rapidly. And that's what the Modeltime program does. So if you go back here where we started this Modeltime workflow and putting it into the table here, this is what allows you to kind of very quickly compare results. We can real quickly just compare how each of these models are doing. And I saw immediately, these two models here were jumping out as the best. So experimenting is super important. Also, we did do a big no-no, and I told you this. I didn't hyperparameter tune. So that's the one other thing that we probably should be doing, is doing some sort of tuning process in here to try and improve these models and really have it as a good benchmark. I do teach hyperparameter tuning in the 203 course for time series. I teach that in depth. And I have a whole module on it. I think it's like 2 or 3 hours worth of video lessons. The importance of experimentation. So what gets a good forecast? You have to experiment. You are going to throw out many of your models. You're trying to look for what are the best models with the least amount of your effort. Your time is valuable. You don't want to waste time trying to improve a model that's doing worse, but rather what's more important is to spend your time on the best models, trying to further improve those to get them to your maximum performance. The other secret is ensembling. So most people don't do this. Ensembling is very important. So depending on your time series, you normally have 3 or 4 different models that are, somewhere near the top. You want to ensemble those. You want to combine them, and that's going to help you get your best results. So that's the importance of experimentation. Try a lot of things out, throw away the stuff that doesn't work, focus on the stuff that does.
Awesome. When you create lag features for the future data lag feature values, okay, let me decipher this. Basically, the question's asking, when you create the lag features, it also adds the NA for the start of it. How do you address that?
So that missing values are actually not that big of a deal for the tree-based models. So, well, I shouldn't say that. That XGBoost, basically LightGBM, CatBoost, and XGBoost can all handle missing values. So you really don't need to address them for the purposes of the forecasting. If you want, what you can do is you can chop those values off because they're always at the end of the series, and we have a pretty long series because it's a daily data set and we have several years worth of data. So it's up to you if you want to try and lop those off, and but you saw that we got some pretty good results and we did not remove those.
Okay. Paul asks, if we use recipes for pre-processing, can the feature importance show the transformed feature names?
If we use recipes for pre-processing, well, they will. Yeah, the feature importance does show the let's try it out. So if we take one of our models here at the end, and I can do feature importance, right? So let's take our best model, feature importance. And if we take the XGBoost model, which is workflow, we want the XGBoost with the defaults, looks something like this. And the script that I have, it'll save me a little typing over here, XGBoost. We just need to extract the fitted model and then do this. So tab over. I think the fitted model is, if I pluck fit and run this, let's see if that works. Oh, I know what I need to do. Pull workflow preprocessor. And why didn't that work? Let's see. That's giving me null. Pull workflow preprocessor. Oh, we don't want the preprocessor. We want the actual model. So we want pull workflow preprocessor prepped recipe fit. There we go. Okay, so it's saying value lag 28 roll 56 is off the charts. So that's a pretty important feature. Date weekday is also an important feature in value lag 28. So the rolling feature was hugely important to this model. The weekday feature and the lag 28. You can see it's got month label 10 in here. So these are the post transformation features. So it is showing post transformation. We can try and zoom in on it. Yeah, it's kind of tough to see. I apologize about the font size here. Okay, so good question.
Okay, great. So let's see here. James has a lengthy question. Let me just summarize it really quick. He prefaces this by saying Gradient Descent interviewed Anthony Goldblum, and they talked about Python and R. Goldblum said that some of the best notebooks on Kaggle are in R. In the beginning, most Kaggle competitions were in R, but now, particularly the notebooks on Kaggle, seem to be predominantly in Python. Now, here's his question. He's wanting to know, are most Kaggle competitions leaning towards Python because of machine learning? He asks a couple of related questions. He wants to know, is Python incorporated into the new course because it's best for machine learning? And he's just confused about if XGBoost is one of the best algorithms, but it's available in R, why is it so much Python focus? So I think it's about Python and R, but he's wanting to know what's the Python leaning.
Yeah. It sounds like he's okay. So let me recap this. It sounds like he attended a talk, and he said, whoever was talking, they talked about Python and R, and he was, hearing them say that there's a transition on Kaggle that's more towards Python on the notebook side, and he wants to know, maybe which one's more important to learn. There is, Python and R, people get too bogged down in that. I'm putting together a course right now in Python. It's, and it's a fun course. I'm having it. I'm excited about doing it. I'm having to learn, stretch myself to learn a lot of new things. Python is definitely a little bit more verbose for certain things. But can you do some of the same things? Well, one thing in Python that I struggle with in building this course is relocating columns. I cannot for the life of me through pandas relocate a darn column. I have to do this. I like to relocate and have my columns in a specific order when I do machine learning. I always have the target up front and I have everything else in the back, and I like to arrange them and do certain things. Tidyverse makes this super simple. They have everything. They have starts with, they have, all of these different tidyverse verbs that makes relocating columns such a simple thing. You think it would be very easy. Very simple. In pandas, it's very difficult. It's really challenging to relocate columns, and it's such a common thing. I don't know why it isn't easier. So my point is, that's just one example, but you hear of the machine learning side of it, and Kaggle, is definitely focuses on the machine learning, and that's important. Getting results often involves building models, but people tend to overvalue machine learning, and they tend to undervalue data wrangling. And what I can tell you is that data wrangling, it's very simple in the tidyverse. It can be, it's actually not that bad in Python as well, but certain things drive me up the wall. And when I want to be able to change around a few columns, I want to be able to do it fast. I want to be able to do it simply, and I want it to do it consistently. I don't want to have to write a for loop. I don't want to have to, try and do some kind of list pop, with a append, and then, no, just, I want to put this column up front, and I want to put everything else in the back. With the tidyverse, it's select that column, comma, everything. Put everything else in the back, and you're done. So that's kind of where I see Python and R. They're good at different things. I think you need to think about what is going to be, what are you going to be doing 90% of your day? You're probably going to be doing a lot of analysis, some visualizations, some data wrangling. You're going to be doing some machine learning, especially in a data scientist role, but that machine learning part of it is probably 5 to 10% of your job. And really, being able, like, if you look at our analysis here, the key really wasn't this part in here, the machine learning part of it. The key was all up here in this data preparation stage, where we had to come up with features, and we had to get this. If we didn't get this feature in here, it doesn't matter what model we threw at it. Like, we needed to get that feature in here, and we did that with this part of it here. So that's why I think R is a really good language to use. In fact, that's why I started using it. Felt good to me. It just made sense. It made things easy to kind of do what's called depliering, taking a piece of pliers to your data and rearranging and wrangling it to get it into the format that you need it to. For this type of analysis, you can do that in pandas as well. It's just probably going to be a lot more code, and that's why you're seeing the Kaggle. Like, if I scroll down here to the bottom, we're at 382 lines here. All of the Kaggle notebooks are like 3,000 lines. So, I like R and I like Python. I'm not, I don't want to hate Python, but Python, for data wrangling, it's not its strength, and R, machine learning, it's getting better. Python, I'm sure data wrangling, it's going to get better too. So that's where I see the two languages.
Okay, great. It's always fun to talk about Python and R, by the way.
Yeah, not really, but
I know that.
It comes up every single time, though.
Yeah, it does come up every time. Well, one thing I will say is, like, the longer you're in technology or working around technology, these types of questions come up over and over as you move through time. There's always kind of a battle between 2 or 3 different technologies, but the key is it's a tool, and some tools might lean better towards one thing versus another, and you use that tool when it makes sense to use it.
And the other thing is that the tools are overvalued too, and you really need to learn how to think Like the problem with data scientists is, and data science in general, is we don't know how to think like business people need us to think. And that is the problem. It's not learning the tools. The tools, you can learn the tools, but if you can't connect the dots and figure out what is the problem, what is the motivation of the business and their need, and then translate that into code, then you're not going to make it very far as a data scientist. But if you can do that well and learn how to think like a real, business data scientist, then that is the power. That's where you unlock, it doesn't matter if you use R or Python. Heck, use them both. I'm going to start using them both now with Reticulate, but it's not R versus Python. It's how can you use R and Python to solve your business need.
Okay, great. Let's see what we got. So Paul was asking, if I want to analyze a bigger data set, I often found Tidymodels tuning took a long time. Many companies are using Spark. Spark has R integration as well. Is that something we can look forward to in a learning lab? R with Spark.
Yeah. Big data is coming up. So I have to kind of figure out what I want to teach there. But Spark is definitely one that, keeps coming up. It's probably also possible too. I have to see how to integrate it into Modeltime, but you might even be able to integrate Spark into Modeltime. So that way you can do kind of like all the big data stuff, like doing the out of RAM. So you use Spark when your data becomes too big for your machine to process it. And what is nice is it kind of manages that for you. But basically, you should be able to link it up to Tidymodels, and you should be able to link it up to Modeltime. So eventually, we'll have all of that stuff in place. But for now, definitely, we'll probably be doing a big data learning lab. I know in the Python course I'm developing right now, I'm going to be covering Dask, which is kind of like an alternative to Spark. But I checked with my students, and they're really excited about learning Dask because you don't need to have any Java dependencies, which is one of the things that you need with Spark. You have to be able to connect it up to Java. So we'll cross that bridge. It's coming. It's on. If you look at the Learning Lab list for this year, right here, Spark for big data, Sparkly R. Yeah, so it's coming. I don't know when, but we'll be doing it.
Okay, great. Let's see if we can get a couple more. There was one question: how would Tidymodel handle and perform the full data set of this competition? And that's kind of in line with what we were talking about big data.
Yeah, I mean, I think it'd be fine. The challenge isn't the full data. The challenge is having enough RAM to load it into memory, which, as long as your computer is big enough, you're fine. Or what you can do is you can chop your data set up and think a little bit strategically about it. Maybe group certain time series together into different files and then create models for those specific files. So, I checked out, I've done a lot of research on the M5 competition, and unless you have access to GPUs, it's probably going to take you about 8 to 12 hours to train your models for the full data set. And you have to have a big enough, you have to have enough memory as well to be able to support that. So break it up, split it up, try and simplify the problem as much as you can, make multiple models. And yeah, you'd probably be good to go. So.
Well, Raj asked a great question. I never seen this before. He says, if you could summarize 2 to 3 concepts to take away from this webinar, what would they be?
If I could summarize 2 to 3 concepts to take away from this webinar, what would they be? Well, the first one, learn Tidymodels. I think that Tidymodels is just a fantastic library for standardizing how to do machine learning. and making it super simple to like swap out basically like components, right? I need a XGBoost model. I'm going to use the XGBoost component. I need LightGBM. I'm going to do that. I'm going to, it makes experimentation, fun, in my opinion. So that's one concept. Let me think about a second one.
Always experiment.
Yeah, experimentation too. Yeah, that's a good one. I think experimenting is one of the things. So I get this question all the time from my students. Can I do this? And it might be like an example might be, can I use ARIMA on a daily data set with 50 observations? And I get these questions all the time, and I like them. I don't mind answering them, but my answer to this is always try it. Like it's the, we're thinking about it like can or can't, and it's like a, binary, but there's gray area, and there's a lot of it, and you need to experiment and try things. And that's what's fun about data science, is that sometimes you get surprised. And I can't tell you how many times I've gone in, with an idea or an assumption in my head, like, hey, this modeling algorithm is going to do really well. And I do, but I try. I always experiment with like a handful of algorithms, like 5 or 10 algorithms. And I always get surprised. I'm like, wow, this algorithm did really well. And I did not expect that. And I've been doing this for like 10 years now. Now the algorithms have all changed, and they've gotten better. But it's just I still get surprised. So experiment.
Great. Depeche asks, from a business perspective, when do we prefer top-down forecasting over bottom-up in hierarchical forecast?
Well, we actually didn't do either well, I mean, we did basically forecast everything.
Yeah.
And this is another type of question that I would say try it, because like there's no rules in my mind. Like you have to, every data set's different. Some data sets, top down might work better than a bottom up. Generally, bottom up works better than top down because you're forecasting the most granular items. But like what we did here was we made aggregated data, and we forecasted both top, middle, and bottom all at the same time. And we made and that's how that's how the hierarchical forecaster, this thing works, is it forecasts them all. All stores, the state level, the store level, the food level, the department level, and then the product level. It forecasts all of those at the same time. So, try different approaches out. There's definitely different ways you could just forecast these, and then you could add them up to get these, and then you can add these up to get this, and then you can add this up to get these, or split them out. But generally speaking, just try whatever way works. The code for this session is now available, or going to be available in Learning Labs. Maybe use that to your advantage and try it on your own data, using this type of approach here.
Okay, great. So we'll do one more. This question says, trying to learn machine learning with R, but I don't have a handle on the theory behind machine learning models. Should I first study the concepts and then learn machine learning, or do both at the same time?
I'm a big proponent of doing both at the same time, because you learn a lot by actually doing. And, you can read all the theory that's out there, and it'll take you a long time to get really like powerful and really understand the nuts and bolts. I'm not saying nuts and bolts aren't important, but when you're trying to drive a car, oftentimes you just need to know, you don't need to know how the engine works, but oftentimes what you need to do is you need to know how each of the functions work, like the brakes, like how to turn the wheel, where the turn signal is, that type of thing. So you can spend a lot of time trying to learn how to build a car, but is it going to be productive? if you just need to drive from point A to point B, and then maybe pick up more information later on down the road as you start to, be driving around. If you hear like, keeping with the car analogy, if you get a flat tire, how to replace the flat tire. You don't probably know how to replace a flat tire, but you should probably learn before you get that flat tire. So, learn that down the road though, once you get started driving. It's not a prerequisite to drive.
It's also a lot more fun to learn both at the same time, because just learning the theory, man,
you're gonna get bogged down
really quick. Nonetheless, we really appreciate everybody for joining us today. It was very active in the comments, so thank you for your interest and participation. And Matt, any final words before we go?
No, I'm just glad that everyone showed up and stuck around this long. I know this was a longer one, but I'm excited for what we've got coming up. And if you are too, if you want to learn stacking, if you want to learn deep learning, we got a lot of good stuff coming. So join us for the ride, and we'll see you next time.
Yep, definitely. We'll see you in about 2 weeks, guys. Take care.
All right. See you guys.
All right. Bye-bye.
Bye-bye.